Hi there, it's Grant from Dome Music Technologies again, and in this video we're going to be looking at the ACE Comparator module called ACE Compare. It's quite a simple module, but it's very versatile too. It has two voltage inputs, voltage X and voltage Y. It has an offset knob for voltage Y, which can go up to plus 10 or minus 10 volts. It has a switch to determine what the condition is that you're trying to work out, and that's where voltage X is greater than or equal to voltage Y, or voltage X is less than or equal to voltage Y. You've got two output sockets. You've got Vx limited, which means that if this condition is not met, then Vx just passes straight through it. But if the condition is met, then Vx is limited to the voltage which is on Vy or the Vy offset. The overflow is just a logic value, so if the condition is met, then a logic 1 is output, which is 5 volts, and the LED will light up whenever the overflow condition is set. So at the moment we're monitoring what Vx and Vy are coming into comparator 1, and as they're both at 0 volts, that means that Vx is greater than or equal to Vy because it's equal to it. So Vx limited is outputting 0 volts, and the overflow is set to 5 to indicate that it's a logic high and the LED is lit up. If we change the Vy input to 1 volt, then we can see that the condition is no longer met because Vx is less than Vy, because Vy is set to 1 volt, and that means that Vx is being passed through it, so all voltages below 0 volts just get passed through, and all voltages above 0 but less than 1 volt just get passed through as well, and then they're limited. As soon as Vx goes over 1 volt, then the Vx limited output just goes to 1 volt, and the overflow output goes to 5, and the LED comes on. Now the Vy offset knob just adds to the control voltage coming in on Vy. So if I set that to minus 1 volts, then that means that Vy is effectively back to 0 volts, and so if we then take Vx limited goes back to 0 volts here, and then if we take Vx to below 0 volts, then it starts coming back out of the Vx limited side of things. The overflow output goes off and the overflow LED goes off. So as well as static voltages, so we'll just take this off, and instead of having a constant voltage, I'll take the output of this LFO, and in fact I'll keep Vy at 0 volts, and then I'll put in a constantly varying voltage to Vx, and I'll just put that to 1 times this triangle wave. So this is the input voltage X. This is Vx limited output, so it never goes above 0 volts, and anytime the Vx input does go above 0 volts, then the overflow line goes logic high and the LED comes on. So we could do the same thing for this second comparator, But what we'll do is we'll change the condition so that Vx, if Vx is less than Vy, then the overflow condition is met and Vx input will be limited. So if we just take that value, set this to 1 times the input and pop that in here. So what you're seeing is that for the half of, in fact I'll just put a trigger signal on that. That's better. So what you can see is that when the input voltage, which is the same on both sides, goes below 0 volts, then this comparator, because the condition is Vx is greater than or equal to Vy, it passes through the negative half of the cycle and the overflow signal goes high when it's being limited at 0 volts in the positive half of the input cycle. You've got the opposite situation in comparator 2 here. So it's the same Vx input voltage, but this time the condition being checked for is that Vx is less than or equal to Vy, which means that whenever the input voltage goes into the negative half of the cycle, the overflow condition is met, it goes logic high, and Vx is limited to 0 volts and letting through any voltages which are above 0 volts. So it's basically a primitive half-wave rectifier that you've got going on here. You can make it a full-wave rectifier by inverting the output of this one. So what I'll do is, instead of inverting the output, I'll invert the input so that, well, let's just see what happens if we do that. Okay, if we try multiplying that by -1, that's what I suspected might happen. So unfortunately, you've got, what's happening is whenever the input to the first comparator is going positive, the input to the second comparator is going negative. So what you're getting is the rectified voltage happening at the same time. What you want to happen is that you get the positive voltage for this part on this comparator and the positive voltage coming out on this comparator. So what we'll have to do is we could do one of two things. We could either change the condition on the second comparator, but what you've got here is two negative going cycles. So if you want it going positive, we'll change both conditions here. And if we mix these two output voltages, I'll just take away this trace here. And if we take the sum of the two Vx limited for that trace, then you see that you've got a full wave rectified unipolar triangle wave. Now, interesting things happen when you take the offset, the Vy signal away from 0 volts. So just try that on comparator 1. So you see that you're getting the top just poking through above the offset signal. And if we, so you can see that the the combined output has changed its nature now. And if we try to put the same offset on here, then we get a more symmetrical type of output. And then if we take that offset down, we get a different type of output. So it's a sort of primitive kind of wave folding operation that you've got going there, which might be useful for some situations. What else can we do with the comparator? We could do a silly sort of thing here. Instead of the gate triggering this envelope generator, we could get it so that it gets triggered by the overflow signal. So if we just take it from this one, so every time comparator 2 goes over the threshold limit, it's triggering the envelope generator. So you can set different threshold levels on different comparators and trigger different envelope generators or percussion generators at different points in the cycle. Get some interesting sort of rhythmical and sequential ideas out of that. One thing that's interesting to do, actually I'll just get rid of a lot of these connections. Is to feed an audio rate sawtooth wave into Vx in. So we've got the sawtooth wave going to the filter here. If instead we take it to Vx in, and on here, if we get rid of some of these traces, and we take the, I'll just up the rate here. So there's the sawtooth wave that's coming into the oscilloscope here. If we then just have a look at the overflow output here, you can see that whenever the sawtooth wave is above 0 volts, you get a positive 5 volts output from the overflow signal, and whenever it's below 0 volts, you get a 0 volt output at the overflow. Now, interesting things start to happen when you increase the Vy offset. So what you've got here is pulse width modulation. And we can hear what that sounds like if we take the overflow output and feed it into the audio end of the filter here. I'll just increase the decay level here. So you see when you get close to minus 5 volts, it disappears in one orientation, and when you get close to plus 5 volts, it starts to disappear in the other orientation. And of course you can use an LFO to provide pulse width modulation. I'll just put this down to 0 at the moment, and then if we feed that into the Y input, make the offset 0. So we've got a square wave just now. Then then if we increase the PWM, and that's controlled by the rate of the LFO. And you can also change the basic pulse width. And adjust the PWM level. So hopefully that's given you a wee bit of insight into some of the applications that you can use the comparator for. It's also useful for arithmetic calculations. Whenever you use the ACE as an actual analog computer, it's a very good way of deciding when a solution has been found to the problem, and it will switch off the running of the program, but we'll leave that for a later video. So hopefully you've picked up a few tips for the ACE comparator through this video. So see you next time.